Today we're going to go over Unit 5 polynomial graphs. We're going to start with the zeros of polynomials. We're going to talk about positive and negative intervals of polynomials and end behavior of polynomials. It looks like Unit 5 just has a unit test, so this looks like sort of a rather long unit, but that's okay. So we're going to start with the zeros of polynomials, and I think this might be review um, possibly when we look at these polynomials. So let me share my screen here. Oops. Share my screen. And we're just going to look at the zeros of polynomials in factored form for this one. So here we see that it crosses the x-axis at 0, 0. It crosses also at 2, 0 and at 3.50. Here we would just say x equals 0, x equals 2, and x equals 3.5. So now we have to figure out which answer choice is correct as far as which one is showing us these x-intercepts. So when x equals 0, that just means an x by itself. So that would be like that, that, or that, because it just is x is equal to 0. Now, when we look at the second part, we set these binomial factored groups equal to 0. So for this first answered choice A, we would say x plus 2 equals 0. And we subtract 2 on both sides, we'd get x is negative 2. Now that's not correct because x equals positive 2 is one of our answer choices. So we can cross that out. If x equaled positive 2, that would be x minus 2 equals 0. And we would, x minus 2 equals 0. We would add 2 to both sides and get x equals 2. So far it looks like B is correct, but let's check the last portion of letter B. So now we're going to set this 2x minus 7 equal to 0. Add 7 to both sides. Divide by 2. And we get x equals 3.5. And that matches our original as well. So this one is B. If we look at these other ones, 2x, if we set that equal to 0, we also get x equals 0. So not that one. And then we would also get x equals 0 for this one as well. Same with D. All of these are just monomials, single terms, and we set them equal to 0 and solve for x, we're just going to get 0. Let's take a look at that. For D, we'll set negative 7 over 2 um, x equal to 0. We have to say x is 0 because negative 7 over 2 times 0 is the only way we're going to get 0. So that's how we do these. Let's look at one more that's not graphed. And go to the next one here. So this one, it doesn't tell us a graph, it just tells us the zeros. So instead of us having to find them, it just tells us what they are. So it says P has zeros at 5, -1, and -1/4. So I like to think opposites in terms of the zeros. So this is going to be x minus 5 represents x equals 5. And you can check this if you need to. You can set it equal to 0, add 5, and we get x equals 5. So that's correct for the first one. X plus 1 equals 0. We solve that for x. We should get -1. And then this last one, let's just double check. 4x plus 1 equals 0. Subtract 1. And we get 4x equals -1. And x equals -1/4. So our answer is B for that one as well. Okay. Okay, now we're going to get into a little bit of factoring with zeros. So for this one, we have to use the AC method, or we can also use the quadratic formula to factor these. So it says plot all the zeros on the graph. So here it doesn't want us to graph it at all. It just wants us to say, where is this crossing on the x-axis? Okay. So first we've got to figure out what degree term is this? The degree term is the highest degree. So if we did all the distributive property, we would start with x squared times x squared, and that would give us x to the fourth. It tells us there's going to be four zeros. Now sometimes there can be the same zero twice, and we can have that like sort of bounce off of a spot on the graph. And so like the graph might look something like this. And then there it would like bounce and then go back down. So those are things to consider as well, but we've got to factor this completely for this part. Let's start with the part that we know though. We know this part here, x squared minus 4 equals 0. If we add 4 to both sides, we get x squared equals 4. Take the square root of both sides and we get x equals 2. So this is going to be 2 is one of our zeros. Okay, now let's look at the next one. We've got to factor this using the AC method, or at least try to. We might have to do the quadratic formula. So remember, all of these quadratics, if they're an x squared, they're in the form ax squared plus bx plus c. We do a times c, which is 1 times 3, and that just gives us 3. And there's only one, well, I guess two ways to get 3 with multiplication. 1 times 3 and -1 times -3. Now we have to figure out which sets of these numbers, if we added them instead of multiplying, would equal 4. Well, it's going to be 1 and 3. So now we're going to write this in expanded form, x squared plus 1x, or just x, plus 3x plus 3. So all these numbers do, and this should be review for most people. All these numbers do is they're breaking down the 4x into an x and a 3x. And we're figuring out how are we breaking that 4x down? What numbers are we going to use? Are we going to use 2 and 2? Are we going to use 1 and 3? Are we going to use anything else? So that's why we do the AC method, to figure out how we're going to break that apart. So now we've broken that apart. We're going to group it, take out the greatest common factor from the first one, take out the greatest common factor from the second one, and then these should always match up. If they don't, that's where you would know that you made an error. So now this is going to be x plus 3, x plus 1, and that's in our factored form. So we have x equals -3. We set that equal to 0. X plus 3 equals 0. That's just -3 on both sides. We get x is -3. And then x plus 1 equals 0. -1 on both sides. We get x equals -1. Okay, so for our up here, the x squared minus 4, I'm going to rewrite that. We already did that earlier, but I'm just going to write it again. Take the square root, and we get x equals 2. Now, for this, now we've got 3 so far. So we're going to plot 1 at -3, 1 at -1, and then 1 at 2 also. Okay. Now you might be thinking, well, there's supposed to be 4 of these. If you notice that, that's correct. So when we take the square root, it's actually plus or minus. So that's the same thing as x equals 2 and x equals -2. So now we have 4 zeros. because if we multiply all of this out, it would be x to the fourth, which means our highest degree is a fourth degree, which tells us we should have four answers. So we're going to have 2, -2, -3, and -1. Those are our zeros for this polynomial. Let's look at one more of these. And this one, it looks like it's a cubed function. And we might have to just take out the greatest common factor of x for this cubed function first. So just going to copy this. And so all these have an x in them. I'm just going to factor out an x or take out an x. And we're left with 3x squared minus 3x minus 18. This becomes much more manageable now. In fact, we could probably factor out a 3 as well. So let's do that. All of these look like they're divisible by 3. So if we divide out a 3, now that's 3 times x, or 3x on the outside. And now we're left with x squared minus x minus 6. We're going to do AC method. A equals 1, B equals -1, and C equals -6. So A times C is -6. And all the ways to get -6 would be 1 times -6, 2 times -3, 3 times -2, and 6 times -1. Now we've got to figure out if we added these together, which of these groups here, if we added them, would equal to -1 or equal to what B is. So we're going to do that next. We're going to figure out which ones equal -1. Well, that's 2 and -3. So now we're going to rewrite this out. 3x on the outside, and this is x squared plus 2x minus 3x minus 6. I'm actually going to put brackets. You don't have to do this, but I'm just going to put brackets so I don't do double parentheses. So we do factor by grouping right here. This is important to make sure that negative goes inside the parentheses. And then we put a plus there. That's really important. We've got to put that plus there. If we put times, that makes a false statement. So now we've got 3x on the very outside. We're going to take the greatest common factor from here. That's x. This is x plus 2. We're going to say plus greatest common factor from this. We want this to be x plus 2 over here as well. So now we're going to factor out to make that a true statement a -3, because -3 times x is -3x, and -3 times 2 is -6. Okay, so now these match up. We're good to go there. We're going to combine them into a single binomial. So the x minus 3, write that one first. And then x plus 2 go second. Now we've got this completely factored. So we're going to set 3x equal to 0. We're going to set x minus 3 equal to 0. And we're going to set x plus 2 equal to 0. Divide by 3. We still get 0. Add 3. We get x equals 3. Subtract 2. And we get x equals -2. So our intercepts are at 0, 3, and -2. Now we don't really know where the graph is going exactly, but we do know where it's crossing on the x-intercepts. Okay, let's take a look at what's next here. The next one is the next one's multiplicity, which has to do with, is it bouncing off of the graph or is it going through? Okay, so this gives us the polynomial. It shows us the graph of the polynomial. Now, anywhere that it's bouncing off of the graph, is going to be an even power. Anywhere that it goes through the graph is an odd power of that zero. So if we take a look at what's happening here at 0, 0, it's bouncing off the graph. So that means that when x equals 0, it's going to be uh, a squared value equals 0, or x squared equals 0. So that means that it's got to be C or D. X squared equals 0. So these x equals zeros, if it was A or B, it would go through the graph. So it would go like the blue line would actually continue this way somewhere. Not necessarily in a straight line, but it would cross the x-axis and go in some direction. So it can't be A and it can't be B just because of those facts right there. So now let's look at what C and D could be. Um, our other x-intercepts are at x equals -2 and x equals 2.5. So this is what we're looking for. X equals -2 and x equals positive 2.5. So we've got the x squared is 0 part down. Now, x does still equal 0. So you might have noticed that it's still going to be 0, but so it still crosses there, but it bounces off because it's a squared term. That's just one of our rules, and this is called multiplicity of polynomials. So now we're going to figure out which one of these binomials is going to make this true. We can actually already see here that the 2x minus 5 quantity squared, that would mean 2x minus 5. I'm just going to say equals 0. And we'll add 5 and add 5. 2x equals 5, x equals 5 over 2, or 2.5. Now you might be thinking, well, that's true. X is 2.5. Because it's a quantity squared, that would mean that it's going to bounce off of 2.5 or go down this way. So it cannot be C either. It can't be C. It has to be D. So for some of these, you can just do process of elimination and figure out, well, which ones have that property of it bouncing off the x-axis and which ones do not. Okay, so let's go to one more of these. This one was D. Let's check out one more of these. And I got to copy these in two parts here, so this might take just a moment. All right, so there's the polynomial. So take a look at where you see anything bouncing off the x-axis while I copy the answer choices here. Okay. Now it says which could be an equation that means maybe the graph isn't exactly like this. Um, but we're just looking at the x-axis. We're looking at the x-intercepts. So our first x-intercept is at x equals -3. Um, that tells us right away we're looking for x plus 3 equals 0. Because if we subtract 3 on both sides, we get x equals -3. So we're looking for x plus 3 equals 0. It's going through the x-axis. It's not bouncing off. So I see that here and here. X minus 3, if we set that equal to 0, that would be positive 3. And we do have another x-intercept at positive 3. So let's actually continue before we start crossing things out. I want to say let's cross these out, but because we've got 3's in both of these, let's just solve the entire problem. So x plus 3 equals 0 is one of our factors. We found that out from this point here. x plus 3 is one of them. And our second 0 is also at 3. Actually, no, there's one right here as well at 1/2. I missed that one. So our next one, we're going to say that's x equals 1/2. Now, if we set that to 0, we're going to minus 1/2 and minus 1/2, and we get x minus 1/2 equals 0. So this is our second x-intercept. This is our second one. So we're going to write x minus 1/2 there. Now, that's not the only way to write x minus 1/2. It looks like we don't have that as an answer choice. We've got 2x plus 1 for all of these. So let's make sure that 2x plus 1 equals 0 also equals 1/2. So if we minus 1/2, I need to go back here just a second. So this should have been, let me go back just a couple steps here. We're going to start this over because I wrote 1/2 and it should be negative 1/2. And if you caught that, that's great. So this should be, I'm going to write this out like this. X is negative 3, x is negative 1/2, and x is positive 3. So let's start this over for x equals negative 1/2. So if we plus 1/2 and plus 1/2, we get x plus 1/2 equals 0. But that's still not on here. We're going to now check these just to make sure that we get x equals negative 1/2 from 2x plus 1 equals 0. So we subtract 1 on both sides. 2x equals negative 1. Divide by 2 on both sides, and we get x is negative 1/2. Okay, so this looks correct for all of these, except not for D. This shows a multiplicity of 2, which means that it would bounce off if it was D, but it's not going to be D. So we're going to cross that one out. But so far, we do know that 2x plus 1 is a factor and that x plus 3 is a factor. I'm going to get rid of some of this stuff now, just so that we have a little bit more room. So our last one we're looking at is x equals 3. If we subtract 3 on both sides, we get x minus 3 equals 0. So our third factor or factor pair is x minus 3. Okay, so this one's bouncing off the x-axis, so that means it's going to be squared. So now let's see if we can match these up. If you might have seen the answer already. It looks like our answer is going to be B for this one also. Okay, so when you're writing these, I made a small mistake earlier. If to avoid that, if you're writing these out, I would just write what the x values are first. That way you know what they are and you're getting the correct answers when you're setting them equal to 0. If you're getting an answer that's an opposite sign, you will automatically know that you need to do some revisions if you write out what these x-intercepts are first. Okay, so that's multiplicity of polynomials. It looks like there's one more section, which is on end behavior of polynomials. And the end behavior has to do with what's happening with the graph as x approaches infinity or negative infinity. And so end behavior has to do with what's going on with the highest degree term. So There's actually a there's actually a chart of end behaviors that I think is really helpful, where you can compare the end behaviors of functions. Um, and I'm just going to copy a chart that I see that we can sort of work with here. I guess, oh, there we go. So here's basically the rule for polynomials and end behaviors. We look at the leading coefficient. So if we have something that's like, for this one, y equals x squared, the leading coefficient or the leading term is x squared. If we had y equals x squared plus 2x plus 5, we're still looking at the x squared. This has a positive leading coefficient. It's 1, and it's positive. It also has an even degree, which means that x is the the power is even. Now, if this was, I'm just going to call this A. So this would be an example of A. This one's going to be, this one's B. For B, it's a negative leading coefficient. So this would be something like negative x squared plus, and I'm just making some of these, the rest of these numbers up here, 5x minus 4. So that would be with a negative leading term and an even degree. We're saying that as x gets bigger, y gets smaller. As x gets smaller, y gets smaller. For A, this is saying as x gets bigger, y gets bigger. Or as x approaches infinity, y also approaches infinity. As x approaches negative infinity, y approaches positive infinity. Let's look at C next. This says a positive leading coefficient, but with an odd degree. So that would be like a positive leading coefficient would be like 3. 3 is a positive number. But now we're talking about an odd degree, so cubic or to the power of 5, as long as that's an odd number. And I'm just going to write it. The rest of this is less important. We're just looking at that leading term. So now with a positive number here and an odd number here, as x gets bigger, y gets bigger. As x gets smaller, y gets smaller. And then finally for D is if we have an odd degree again, but a negative leading coefficient. So if we have like negative 5x cubed, so an odd degree, x cubed, negative leading coefficient, negative 5 is our leading coefficient. And then again, the rest of the polynomial, much less important. We're just looking at the first term. So now as x approaches negative infinity, as x gets smaller, y gets bigger. And as x gets bigger, y gets smaller. And we can even write tails in the graph to show that the direction that they're going in, if that's helpful too. So these are just the rules of end behavior of polynomials. Right, D here. Okay, so you might want to take a screenshot of this just to save these examples if that's helpful for you. So now you have the rules of the end behavior of polynomials. I'm going to actually there's a better screenshot for you if you need to do that, or if the last one works too, that's great. I'm going to erase this, but I'm going to leave this chart here, and we're going to answer some questions on end behavior that ask us to, it looks like a lot of reading, but it's not too bad. I'm going to go to the next question on my questions here. Okay, so yes, it's possible to graph these on a graphing calculator and see the answer, but the point is understanding what end behavior is and understanding the rules uh, of of the function. So let's take a look at this one. It says, consider this polynomial function. We have x to the sixth minus 3x to the fifth minus 17x cubed. What's the end behavior of the graph? X to the sixth is uh, our leading coefficient is positive, and our degree is even. So for this one, we're going to look at graph A. Once you know that, now you can figure out what are these rules saying? Well, as x approaches infinity, y approaches infinity. That's true right there. That's the first statement for A. The second statement for A says as x approaches negative infinity, y approaches positive infinity. And that's that statement there. So this has to be A for this one. If you look at the rest of these, they're not going to match up to the rule for A with a positive leading coefficient and an even degree. Let's look at just one more of these, because again, once you have this chart, you can make references to the chart as well. If you're going to be tested on this later and you don't have a chart, well, just try your best to remember the rules of what's happening. If you think about it in terms of just this A and B is x, this is, if you think about it like that's x squared, that's negative x squared. This is x cubed, and this is negative x cubed. If you think about it sort of like that, that helps you to apply the rule and remember the rule a little bit better, I think. Okay, here's the last one we're gonna do. Uh, it says p of x is negative 9x to the ninth plus 6x to the sixth minus 3x cubed plus 1. What's the end behavior of the graph of p? Negative 9x to the ninth is what we're really focused on. We have a negative leading coefficient, and we have an odd degree exponent. So that means we're going to use D. So now let's just check to see what D says. So instead of going through A, B, C, and D, I'm just going to look to see which one matches. As x approaches negative infinity, y approaches positive infinity. So as x approaches negative infinity, y approaches positive. That looks correct for A and for B. So we can cross off C and D right away. The next component of graph D is as x approaches infinity, y approaches negative infinity. So as x approaches infinity, y approaches negative infinity. Cross off A, and it looks like our answer is B for this one. Okay. All right, so that's everything with polynomial graphs, with the zeros of polynomials and behavior.